this for doing all the paperwork. So appreciate all the pain you took with doing that. Now, it's been an interesting week, and the talk today is written to be a bit divisive. So it seems to be the flow and the feeling of the moment. So we'll see how this goes. I gave a similar talk in New Zealand a few years ago, and one of the things that came out was, at least for me, how much we think we know, but in fact we don't actually. And how much we think climate, big topic, is impacting, will be impacting our lives, and what at least we know or not know at this point about what that actually will be. So we'll talk a lot about costs here in our economists, so there will be some numbers, and we can debate these numbers and how good or bad they are. So I'm going to start with actually you. So I'm going to ask you a question, and the question is, by the end of the century, how much do you think climate change will affect, positively or negatively, GDP? GDP is a measure of the economy, so you can give me a number between 0% as a cost. You can go negative if you want to, if you think it's a good thing. But let's say 0%, no cost, until 100% of GDP is going to be affected by climate change. So I'm just going to need some volunteer to start us to give us a number. Global GDP.
By the end of the century.
End of the century. Yeah.
I think GDP will be ruined as a measure.
Fair, different debate, but let's stick with GDP.
Well, we're going to talk about the measure, or we're going to talk about like what price to measure.
No, so right now I'm just trying to get, we'll talk about all these things.
You want to know what price?
I just need a number, so to see, how that number shapes up with our best estimate at the moment, which we can debate how good it is. But so right now it's just the number I'll need.
Negative 70%.
How much?
Negative 70%.
70%. Okay.
Say negative 15.
15. Where is this going to go?
60%.
60%. 15, 60, 70. Anyone wanting to do like single digits? No? Okay, so let's go with this. So between 15 and 70% of GDP.
Which is negative 70.
Yeah, and cost. The cost. Yeah, no, nobody is going to predict the benefit. You want to?
I mean, if you talk about, I know Nordhaus says crazy things like it's only gonna, agriculture is like 2% of GDP. If we lose all agriculture, that's not a big hit to GDP, which is obviously insane. But if you count like adaptations and having to build back after climate catastrophes, that could, be counted as an increase in GDP in some ways. But obviously, I agree with my esteemed colleague here that it's not the best, unit of measurement.
Sure. Okay. So we're sticking to between 15 and 70% of GDP globally destroyed by the end of the century because of climate change. We'll talk about numbers and we can debate how. Cool. So let's see what currently the best prediction is that we have. So I'm going to start out by my favorite tweet about this topic. And I did this presentation before Tuesday, so just as a disclaimer. Yeah, I like the tweet. I don't know if it's meant as a joke or not, and I'm not going to take a stand on that because I have a return ticket. But yeah, there's always a confusion between weather and climate, right? We always don't really know what that is, and people have very different experiences of that trade-off. So just to fix our thoughts, not that I think that anyone has a problem in here, but when I was a teenager, people weren't talking about climate change. People talked about global warming, and that was a thing. So most people believed. So now it has changed to the framing of climate change for reasons I don't quite understand, but that's okay. Climate being the long-term average of weather, loosely defined, and current normal climate is 91 to 2020. Or if you like it more technical, again, as an economist, we like technical stuff, climate as a distribution of weather. Okay, and we'll come back to that in a minute. So that's fixing our thoughts, and there is just a nice graph of temperature to kind of visualize what we're talking about. High frequency gets averaged out, and we're talking about this is stable, this isn't, something's going on. Okay, cool. Now we know that that's your greenhouse gas emissions, so we can look at CO2 here over a long time horizon, and nobody's going to, wonder what's going on here. All of that is man-made. Well, at least a large part is man-made. No questions about that. And then we can talk about surface temperatures wobbling around, but clearly something is off here. Cool. So we know all of that. We can look at temperatures here or rainfall on the next slide, I believe. Again, this is man-made. Nobody's going to well, I hope nobody's going to disagree with that. At least they shouldn't. That we see here, we have simulations without human interference and with, and we clearly see that one model is rejected. So not much that there should be a debate about this. On the other side of this is the predictions. And that's where things get a little bit more tricky. Turns out that, so these are our observations, this is where the data stops, and then we have climate models that predict and the 9% significant intervals around that. Now, it turns out these are extremely wide, right? So it could be, by the end of the century, maybe a degree, maybe 3 or whatever, under this scenario, under the model assumptions, we can debate. On average, we're probably looking at 2 points under this assumptions. Great. But the uncertainty, and that's something that I'll come back on, is quite large. And if you're a policymaker and you believe we are here, your actions will be very different than if you believe we're over here. Right? And that's part of the debate that we having, or we at least should be having. How does this uncertainty matter? Now, the title of the talk is not a typo, it's warming worlds. Well, there's just one. We all live in a very different world, right? We have some professors in here, we have some PhD students in here, just by income, we're living in different worlds. Now, there is infinitely many heterogeneity here that we have to think about when we talk about climate costs. Just at the very, to visualize that somehow, you have changes in temperature, changes in precipitation. We are somewhere here, if my geography is correct. So we're looking at something like that based on this model and so on. I'm from Germany. We're over here looking at 1-ish degree. I live here down here in New Zealand. That's probably around 0.5, 0.75. So if you're looking for a job, that might be a good place. My girlfriend's family is from Chile, so that's about here, looking at a degree. And then again, you can see that there are spots that get way warmer than that, but there's huge heterogeneity here where you are relative to the equator and so on and so forth. But yeah, massive differences just in temperature, which is one of the variables that we're interested in, and the same picture there for rainfall. And huge heterogeneity in the impact of climate, therefore in the costs that these populations will be experiencing. And we need to figure it in somehow. So we'll have to talk in a way about the inequality in costs that people will be experiencing, or populations will be experiencing. Like states in the US, Vermont down here, 65F, and then by the end of the century, we're looking at Vermont over here, 75 for this model, and so on and so forth, all the assumptions built in, but just to give you a bit of an idea of where things could be going in the future. So all of this shifts to the right, meaning everything gets warmer. Okay. Again, this is June, July, August average temperature, big picture, that'll happen. Okay. Whether it's 65 to 75 or whatever, it's just going to
full stop. But again, huge heterogeneity in there and in exposure to these climate variables. We could do this for rainfall, for disasters, whatever you like, but it's going to take more. But then to the topic of what we think we know, or what we think the evidence is very strong of is, as an example, and I only have 30 minutes, in this case, tropical cyclones. And then you read something like the IPCC, which I like to read, and often you wonder that the statements, at least I wonder, that the statements are not stronger than they are. Now, what these statements say is there's low confidence for this example here that there is any long-term trend in tropical cyclones, intensity, frequency, whatsoever. Now, it doesn't mean that that is not happening. It just means that we have low confidence. It's just very noisy to estimate these things. And then we look at time series graphs here, whether it's frequency or energy of these events. And sometimes, at least I wonder where the trend is that I would expect to see. And you know, it's not in these, whether it's global, whether it's Northern Hemisphere. So sometimes I think there is a perception that the evidence is stronger than what it is. And that feeds into cost calculations. Because all these models, so this is observed data, but that goes into the models which are predicting 100 years into the future. So lots of uncertainty around how we put this into a model with a lot of different kinds of uncertainties that spit out projections. So we'll come back to that when we talk about the 15 to 70% GDP cost. And then there's also the issue that sometimes reading these climate papers, as an economist maybe, you wonder about some of the choices that people make. So here's a very influential paper by Frederikse, I think, in Nature about global mean sea level. And this is very interesting to look at because they take averages over time periods. Okay? So they say we'll take the average from 1901 to 1971, this average, and then we tell you increase in GMSL. Problem with that is, as every first year statistic lecture probably does, if you take an average over this thing versus an average over this thing, it's a very different animal. Right? I'm not debating that this isn't true. I'm not debating, that there's anything wrong with this. I'm just saying it matters how you present your data. And here the averages are very low. Here the average, because this is technically non-stationary, right? It's drifting. This average here is going to be very different. So we need to be very careful how we present them, because once we look at this, we say, well, okay, this increase here is probably not significantly different from this increase. And that's a very different takeaway from the rate over this period is different from the rate over this period. We're not debating this is true, just saying we need to be careful how we communicate these things. Okay. So sometimes you look at these, I look at these things, I'm a little bit surprised how people present it. So let me get into costs. And I like to kind of fix our thoughts. And Meredith, the first time I was here, told me that don't use equations. So I'm not using equations, I'm using a figure. Okay, so using a figure here. And you get some idea of how we think about, how economists think about what are climate costs and how can we compute this. Right, so lots of graphs, I'll talk you through this briefly. This is the distribution of weather, which we call climate. Okay, so the blue one, or climate one, is it's our distribution of climate. Now, then time happens, and in each month, we draw a temperature realization. Okay, so the month of November has this temperature. Cool. And then as time goes on, stuff happens. Right? Every month has a different temperature. Cool. So this is kind of the climate side. We want to get from the climate side of things to something like an economic outcome, mortality, yields, whatever you like. Okay. No, so we have to map the climate variable to some economic, socioeconomic outcome. How do we do this? Well, we come up with these damage functions, dose response functions, different names for these animals. But nevertheless, at a very basic thing, it's if temperature is this, the climate outcome is that. Great. Now, again, do this over time. You map temperatures to these climate outcomes, and you get mortality, for example, heat-related deaths, and that's moving around. Okay. And if you want to, you can make a distribution over, in my example, mortality over the climate. Now, what's climate change? Well, we have a different climate. And in this case, if it's temperature, it's shifting to the right, and it stretches. Now, different climate means different weather. Ignore the second one here, the kind of pink F2 of X. That gives us a different mortality series over time, okay? Or a different distribution, it's hard to see here, but it gives you a different distribution of the economic outcome variable that you're interested in. Now, what's adaptation in this? Adaptation is the change of this curve. So if this curve is changing, then you have differences in between the blue and the pink line. Okay? And that will result in a different outcome distribution here, meaning different costs. Okay? So this is the effect of climate change, a change in the climate, and this point here is where adaptation happens. And obviously we want to have an adaptation where if this is a negative outcome, like mortality, we want to reduce it, obviously. So that's how we think about it, how we would model how the climate links to any socioeconomic outcome that we want. Okay. Now, the problem with these curves is we don't really know what they are. And there's multiple reasons for that. The first thing is, well, it was drawn non-linear. How non-linear? No idea. Is it continuous? No idea. Or are there actually two of these? Or if we think about multiple populations, does any population have a different damage function, dose response function? Of course, we estimate these things and we come up with the best guess, but overall, we have no idea. Right? Huge uncertainty in these things. So that matters for adaptation, that matters for cost calculations, that matters for everything that is climate to socioeconomic. So huge uncertainty. We're not talking about uncertainty in climate, we're talking about uncertainty around how the climate affects the economy or socioeconomic outcomes. So that will be what we would call modeling uncertainty. It's not just even parameter uncertainty, which is what's the slope of this thing? That's parameter uncertainty. It's modeling uncertainty, which is even worse because there's no idea. So then the uncertainty that we already talked about a bit is represented here in what I think is a very nice graph. You have early years, then you have like the 15 to 22 years, which are kind of bunched together. It's hard to tell a difference here, but then you got 23, which is clearly shifted to the right. There's no overlap here, so this is clearly different. Okay. Again, the distribution is shifting here. It's not just that we're shifting to the right, we're also stretching this thing. So it's very different to calculate just the change in temperature, like from 1.1 to 1.5. If also the distribution is shifting, cost calculations become even more difficult because you get second order effects. And that relates to predictions, especially for economic predictions. Now, we can debate how the climate models are. Climate is a slow-moving thing over long horizons. Maybe it's reasonable or not. What I want to talk about is the prediction of the economic system underlying. And there, a hypothetical here is, suppose you're living in 1918 and you predict the economy or the impact of CO2 in 2018. Now, first, that was already a question at the time. So there's an article in Quarterly Journal of Economics in 1917 about agriculture and carbon emissions, how that's going to go. So you would think that, well, okay, that's great. In 1918, the most famous car was the Model T, which had 18 miles per gallon. I think my Prius now is probably better than that. Most people were on steam trains. If he wanted to go to London from New York, he would take, I think, the White Star Line, which takes about 7 to 10 days, and most people were on horses. Now, I'll bet you nobody could correctly predict the economy in 2018, and Teslas and the internet, and well, AI wasn't quite a thing there, but there's no way you're going to predict that. So, us now predicting 2018 to 2118, and how the economy is looking and how the costs of climate change will affect that economy is confidence intervals this large. So I will give you a number later, but I'm already going to say that number is wrong. Okay, it's our best guess, but the number is wrong because there's no way you can do this. No way. Okay. Now I always tell my students, even if you have no model, even if you have a bad model, it might be better than having no model. But we need to be careful in how we interpret the outcome of this. Okay? So that's the important takeaway. So this is pretty much how I started about what we think we know about the impact of climate on everything. And I don't want you to read all of that, but this is pretty much what we actually know. A little bit exaggerated. And it's usually just about temperature and rainfall impacts. A little bit about storms, but generally, that's the kind of magnitude, if you look into the literature, that we see. This is what we think, or at least want to know. This is what we actually know, what we're pretty sure of. Now, let's talk costs. Now, again, these are the best estimates that we have. I'm not saying these are good estimates. I'm saying these are the best estimates that we have. Different models, different assumptions. You have temperature on the horizontal, you have global GDP impact on the vertical. So these are negative numbers. So these are going to be the costs. And so the best estimate right now, pick any number of temperature that you want for, let's say, -2. So this is the best number that we have. I'm not saying it's a good number, I'm saying it's the best number that we have at the moment. That's one study. If you want a different study, this is for the US, same number. I said 4 degrees is about 3%. If you want higher temperatures, it goes, I don't know, 5% goes to, 5 degrees goes to 5% of US GDP, same time frame. That's the best numbers that we have, and you can cite different papers. This is what you're, right? Ballpark. Where are these costs? Mortality. Where are these costs? Ag. Where are these costs? These are counties in the US ranked by income, and you can see that these costs are not the same. So some counties, states, will be very differently affected than other counties, states in the US. Again, heterogeneity. Heterogeneity in where you live, heterogeneity in where you work, heterogeneity in the kind of costs that you're facing. But again, this is kind of the total impact of that climate impact. So let's have a look at these numbers and think about the dimension, magnitude of this effect. So IPCC says 3.7 degrees by 2100. And they say global GDP goes down by 2.6%. Roughly ballpark of what we've seen. Extreme assumptions in these models, 5% of global GDP. Right? Let's stick with 5% as kind of the worst case of these simulations. Now, 5% of GDP, even though it's smaller than the 70 and 60 and 15% that we had in here, is still a very big number. It's $1 trillion today. That's a lot. Even for Bezos, Musk, and Gates, that's a lot. The problem with that is it's extremely misleading because it's not $1 trillion today. It is 5% in 80 years. And 5% in 80 years is a very different animal. Why? Well, let's say the US is growing at 2%
or I'll give you a 3% number higher, annually higher, annually over this period of time, which is kind of on the low end of what the US economy did. But yeah, fix our thoughts. That means by the end of the century, you, well, probably your children and your children's will be 400% better off in 2001. That's the effect of compounding. Now, to put that magnitude in something that we can understand, because 400% sounds like a lot, that means that if this number were right, 5% is 3 years of lost growth. That's a big recession. GFC effect was 4 point something in the US, COVID recession, 5 point something. So this is basically a large recession. You could also say that if this were not, there were no mitigation, no adaptation, you are by 2100, or children's 380% better. So the $1 trillion today is a very misleading number. It's large, but it's misleading. You really need to compare these two things, 400% to 380%. Not saying this is small or this is large, I'm just saying this is what it is. Okay? In the best estimates that we have, those are the costs of climate change. So in 2100, you or your kids will be living at 2,970 levels of GDP with climate change. Okay, so that's what the research at this time tells you, what the impact is going to be. We're going to look at growth. That's something that people are usually interested in. US is over here. You get this nonlinear response, which there is some kind of behavioral mechanism related to that. I'm not going to go into that unless there are questions. So here's the US moved to the right, little effect on growth. Little effect on growth. If you're to the left of this, you're actually benefiting. If you're to the right of this, you're going to be losing. That is countries which we would generally describe as poor, certainly relative to the US. But this is a big chunk of the world's population. A big chunk of the world's population is going to be in this part where increases going to reduce your GDP by a lot. Again, this is highly unequal. This is an example of exposure to tropical cyclones. Here, this is the poor regions of the world, which will experience this cumulative, which will experience the biggest chunk of tropical cyclone effects. It's not you, right? It's not the US that's going to face most of the costs associated with this. So highly unequal. Weather-related disasters and that, again, going down. We can talk about data quality, generally going down. Heat-related deaths, something that I find in this debate is very misleading because we only look at this. Heat deaths. Heat deaths are increasing if temperature is increasing, right? Nobody tells you that this is where most of the deaths occur in cold-related deaths, and that's actually getting better up until about 4 degrees, if you want to believe the estimates. Highly unequal. This is data for Europe. Highly unequal because this is almost entirely in the population of 75 years and older. Right? These are the people that are affected by cold deaths as well as heat deaths. Highly unequally distributed. Right? The costs are very unequal. Global deaths of climate change. Right? You are here, high income. You know, might be positive, but most of the math is negative. If you're in a poor country, biggest increase, right? Poor correlated with hot, increases in temperature, increases in cyclone activity, all these things. Highly unequally distributed. Floodings. I know Vermont has experienced lots of flooding. Again, cost estimates in here. If you look at costs in dollar is going up. Costs in terms of how rich we are is not much anymore. Depends on how we think about costs. Is it dollar value or is it in terms of how rich we are? You can pick what you prefer, but it really depends on where you go.
Why is that? Let's look at the example of hurricanes here. One of the stories that is always told is, well, the cost of hurricanes is increasing, which is true. Problem is, house prices are increasing. Populations are growing. We're building houses where there are storms. So if these storms that happened here would occur at today's value and today's population, there isn't much of a trend in there. So if we talk about costs, we have to be very careful how we count these costs. Because yes, this is what happens here, but the underlying populations are changing. And then to say, oh, these costs are purely because of climate change is wrong. It's also because underlying changes happen that go into the calculation of how these costs are calculated. So very important. Many other topics we can talk about, you can ask questions at the end, from everything from conflict and crime to cognitive performance, labor productivity, mental health, all of that is going to get worse. Okay, so the direction is clear in these studies. One thing I have been thinking about and find hard to understand is, and there's little research on it, there's more and more coming out, but that's climate anxiety, or eco-anxiety is something that's called. And the idea here is, so some people have done work on this, and this was a very, very, in a way, frightening survey. So this was 10,000 young adults across the world in countries, rich countries, and they reported that 75% of these people reported that they're frightened of the future. Frightened. Now, chances of someone dying in Austria because of a climate-related death are very low. They're not zero, but they're very low. So to say that these people are frightened by it, if you think about the mental health effects of that, is just probably gigantic. Okay, gigantic effects, and there isn't much research on this. There is research, but I think how important this is, there isn't that much. So let me just wrap up so I don't get into the doghouse. Global warming is real, it's man-made, but we're not ending. It impacts our lives right now and will so even more so in the future. The costs or impacts are extremely heterogeneous. Probably everyone in here is on the lucky side of things, right? If I, in my house, if temperatures go up in Otago where I live, I'll put an AC in my house and I'm fine, right? Other populations aren't that lucky. So that's one of the biggest problems, in my opinion, in this entire literature, that we don't have any idea about the distribution of these costs, okay, from climate change. Climate models are terrible for regional predictions. Basically, forget it. The best numbers that we have right now, again, best, not correct, is that by 2100, you'll be 380% better with climate change in the US. The problem in there, to me, is not the climate uncertainty or risk, it's the growth risk because of the compounding. The growth rate is not 2% or 3%, but 1 point something. That number will change more than whether you're 5% or 10%. Okay, so that's a big thing. Adaptation costs, small, not for you and me, but for in terms of the entire economy. An example, I was just been to California. So wildfire budget in California is $3 billion. Sounds like a lot. Actually, it's 1% of California's budget. It's not that much. 1.1% of the GDP of California. Not that much. They're building or planning to build a high-speed train. It's about $100 billion. So, you know, sure, for you and me, that's infinitely many money, but in the grand scheme of things, these costs are not that large. Of course, it's just wildfire, there's other things I'll get. To me, the debate should not be about economic costs. It should be about preserve the environment. It's as simple as that. Species extinction, air pollution, water pollution, access to water, clean water, I should say. Huge problems, which kind of gets dwarfed by people coming up with numbers of what GDP decrease will be, which is wrong in any case. So I don't think we should be talking about this at all. we should be just saying, look, do you want to live in a nice environment? Yes or no? And if the answer is yes, well, we should do something about that. Economic system overall, that's going to be fun to debate, works well, except that our aspirations seem to be driving faster than what the system is changing. Okay. What we need, this is kind of my wish list, much better climate models at the regional level and incorporating economic systems, which are bad, better communications, accurate and balanced, thoughtful decarbonation, economists like carbon taxes, not exception, respecting the developing world, because we are rich because of cheap energy, and if they want to get out of poverty, they need cheap energy. Adaptation, you can read that, green RD, geoengineering, something I don't understand, but I see the potential. That's kind of my wish list. Overall, if I think about these climate costs that are there, or ask me to put a number on, I have no idea what they will be by 2100. There's so much uncertainty from the climate side, from the economic side, that coming up with a reasonable number is just best guess. So we have 15, 60, 70, maybe that's right. The best estimate that we have this moment is 5%. And then from there, we can calculate what that is. Now, again, basically the conclusion of the talk is this bullet point I should have left on that. It's really not about economic costs, because we can't predict them. Forget it. It should be sufficient to say that we want to protect them. And I'm going to leave it at that. If you have other questions on that, we can debate that, but I think I'm already over time, so I'm just going to stop.